test. 1, 2, 3.
I can hear you, Professor.
Yeah, hi guys. So we'll get started in about 9 minutes or so. Okay, so I will record this. I will post this on Blackboard. And in addition to that, so let me share my screen one more time. And let me temporarily bring this up instead. Let's see here. If you look at the website, there is a folder with all the recorded lectures from the previous semester. And so if you go in here, this is the S21 lectures. So this would be equivalent to lecture number 2. So you can always review this too to get a slightly different tilt on it. And it's a YouTube link. And in this one, I actually have a little video that one of my former students, Nolan Manteufel, did a little soldering, a very quick soldering demo. I am going to do a little soldering demo as part of the one today, but you can always look at this and get a slightly different twist on it. All right, so here we are. So basically what I want you to take away from this course, and let's see, I'm not seeing myself, so let me go back here. Oh, well, I don't know, it should. I don't know. All right, well, maybe it just won't. You guys can probably see it. It should show up here. I don't know why it's not doing that. Oh, there we go. So maybe we'll do that. Okay. All right. So anyway, what I want you to take away from this course is a basic understanding of microprocessors. I want you to have a pretty good handle on the particular chip we're studying and have a level of confidence that you could take another chip and spend some time, learn whatever the appropriate integrated development environment for that chip would be. Might be if it's a microchip product, it might be MPLAB-X, but if it's not, it's probably something else. For the NXP products, we use MCU Expresso. For Intel products, we use their interface. Many of the chips that have ARM cores on them can use third-party interfaces, and there are third-party interfaces even for the PIC stuff. So you can kind of take your pick there. But once you've learned one integrated development environment for a microprocessor, and once you've learned the instruction set for one microprocessor, and then learned how to interface it, how to program it both in assembly and then in C, primarily you're probably going to program things in C. But the reason that I have you do the first 4 or 5 labs in assembly is because I want you to use assembly language, because that's what C gets translated into for every microprocessor. Now, every microprocessor's assembly language is different, has a different instruction set and whatnot, assuming that they're not in the same family, which there are plenty in this family actually. But once you understand one, you understand all the others because they're all very, very similar. All microprocessors have very similar components. Some are just a whole lot more complex than others. And if you understand, and it's easier to understand a simple microprocessor the first time you really look at it, and that's why we're using this one. It's an 8-bit, fairly simple, but still very powerful chip. It can execute something like 8 million instructions a second. That's a lot of instructions. There are ones that can execute more. This one is Harvard architecture. A lot of the microprocessors are von Neumann architecture. We'll talk about the differences there, but that doesn't really matter because there are plenty of other, even ARM core based processors that are Harvard, and some that are von Neumann. So learning one or the other it's not really a big deal. If anything, learning the Harvard first sets you up to understand all of them because it's the one that's a little different. And the von Neumann's a little more straightforward. Okay, so let's dig into it. So we talked in logic design about layers of abstraction. So when you program in C, you generally ignore the assembly language level of abstraction. You just don't pay any attention to that. You just write your program in C, and then the compiler compiles the assembly gets assembled, gets loaded in the chip runs. But if you have a problem with how it's executing one of your C language instructions, you might have to get down in the details. And when you get down in the details on the chip level are assembly language. They're machine language, which is just assembly language translated into numbers. So, but C, a single C instruction can be translated perhaps into one single assembly language instruction, or a single C instruction might be translated into 20 or 30 or 40 assembly language instructions. So because of that, you do have to, you have this layer of abstraction between you and what's really happening when you program in C. And at some point in your life, you need to have pierced that veil and taken a good look, because you're going to be computer and electrical engineers. That means you understand the circuits as well as the software. Whereas if you're a computer science major, you don't. You understand the software, but you don't understand the circuits, which means when you want to hook this chip up to some other real world devices through programmable pins, that's a whole nother level. And if you don't know what's going on down at the basic level, there may be some things happening that will totally confuse you and blow your mind. But if you do understand, you'll be able to figure it out and make get your design completed. So that's why I have you do this. And there are opinions divided on this, but I think if you talk to the vast majority of educators out there, most of them will agree that if you never have looked at assembly language, you don't have a complete picture. It's just that simple. And you're missing some tools from your toolbox that you should have. All right. So anyway, so I want you to understand the basic architecture of this 8-bit PIC chip. And so we're going to go over that. And that's because these architectural features are replicated in every single microprocessor ever made in different ways. They may look a little different. There may be more of them. They may be implemented slightly differently, but all the pieces are going to be there. There just will be some differences. So once you understand one chip, you really have a window into all chips. For this particular chip, there is some program memory, which is implemented in Flash, which is a type of read-only memory. And then there are some random access memory that's not ROM, that's RAM. And then you have some special function registers, which allow you to make the chip work and use all the peripheral devices. And the program memory is in a separate memory area, and the data memory and the special function registers and all the core registers are all in a separate area. And that's what makes this a Harvard machine. And it turns out there's a separate address bus for the program memory and a separate data bus for the program memory from the address bus for the data and special function registers, and also a separate address bus and data bus for both. So you have two address buses, one for the program memory, one for the data and special function registers, and you have two separate data buses, one for the program memory and one for the data and special function registers, which means you can be moving things at the same time on these different buses. So that's sort of an advantage. The other thing that's interesting is the program memory, every location in the program memory is 14 bits wide. And the data bus is 14 bits wide. And the address bus has 15 bits. Now, it's not all used on this particular chip, but this family of chips, there are some that use most, if not all, of those 15 bits. On the data register side, you have 12 bits of address in the address bus, and you have 8 bits in the data bus. So the data bus is much smaller, almost half the size, and the address bus is also 3 bits smaller. So it's only 12 instead of 15. So on the program memory side, you can have up to 32K. On the data memory side, you can only have up to 4K. Is that right? No, I guess it's no 12. It's yeah, 11 would be 2, 12 would be 4. Yeah, 4K. And so that's the maximum program memory space in this family would be 4K. 12. No, I guess it's 0 to 12. So there's actually 13 lines. Yeah, I don't know. I'll recount them in a minute because I think you can have up to 8K. So there must be 13 address lines in the data memory. No, maybe you can only have 4K. Yeah, okay, I think that is right. 12 bits. All right. So anyway, we'll get to that. So just remember, the point is separate program memory and data and special function memory with their own address bus and their own data buses. All of the peripherals, and a peripheral would be like an A to D converter, a timer, a comparator, a touch sense module, a timer, I don't know, a PWM module, UART, all sorts of peripheral modules. And all of the control registers and data registers for these peripheral modules are mapped into the data and special function memory. They're not in the program memory area, they're in the data memory area. The data memory is divided up into 32 banks. And there's a bank register called the BSR, Bank Select Register, that holds which bank you're currently pointed to. And whenever you want to deal with a different bank, then you have to change that register, as well as you have to have obviously a different address in your actual instruction. Every microprocessor has what's called a programmer's model. And the programmer's model, when I first started writing programs, nobody talked about programmer's model. It's kind of something that they came up with later on and sort of applied backwards to the existing hardware. So when I first started writing programs for, say, the 6502 chip, I didn't know about the programmer's model, but I did know about the registers that were involved in the workings of the chip. And that's all the programmer's model is. It's just a fancy name for the registers that the chip uses to do its thing. So some registers are just normal memory locations, and some registers are special in that the actual guts of the chip use those registers for every instruction over and over and over again every time. So some registers are really busy, some registers are not very busy at all. And in this particular chip, it doesn't have very many registers in the programmer's model. It's a simple chip. There are chips that have quite a few registers in the programmer's model. We use Freedom boards for Micro 2, and in Micro 2, the general purpose registers, there are 13 general purpose registers. On this chip, there's one general purpose register, and it's called the W register, which stands for working register. And we normally just write W when we refer to this. The program counter is also a register that every single microprocessor has. Your desktop, your laptop, all the embedded processors in your automobile, all the embedded the processor in your cell phone, all the processors that I'm aware of, all the microprocessors, all the microcontrollers, all the microcomputers, they all have a program counter. And what the program counter does is it points to the next instruction to be fetched from the program memory for the chip to execute. Now, because even in this chip, we have pipelining, it's actually pointing a couple of registers ahead, so that when you get a branch, you have to flush out the pipeline and reset the program counter to point to the right register, and then away you go. So anytime you take a branch on this chip, you burn one instruction cycle. You just waste it. So the more branches you take, the more instruction cycles you're burning, but the more efficient use you're making typically of your program memory. That program counter is automatically incremented to point to the next instruction every time it fetches the current instruction. And in this particular chip, because the program memory has has up to 32K, so it has 15 bits. This program counter is a 15-bit register. It's not a 16-bit register, it's only a 15-bit. And it's divided into two parts because in this chip, we can only move 8 bits at a time on our data bus. And so when we want to load the program counter, we have to do it in 2 separate bytes, or one byte only has 7 bits and 1 byte has 8 bits. And the way this works in this chip, which is a little goofy, but this is how they did it. There's a register called the program counter low. That's the lower 8 bits of the 15-bit program counter. And again, the program counter is pointing to the next instruction to be executed, with a caveat on that is actually in actuality, no, it's really not doing that. It's pointing a couple ahead because there's pipelining. But don't worry about that. You worry about the big picture, which is it's pointing to the next instruction. And when you want to point it to a different instruction, you can actually load the address of that instruction into the program counter. But you have to do it in 2 steps because you can only move 8 bits at a time, and it's a 15-bit register. So the first thing you do is you take your upper 7 bits of your new address and you put them into this special register called the program counter latch high, PCLATH. And that program counter latch high is the upper 7 bits of the 15 bits in the program counter. You cannot write directly to those upper 7 bits. You have to first preload them into this program counter latch high. And then you write the lower 8 bits into the program counter. When you write the lower 8 bits as a second step, having already preloaded the latch, the hardware in this chip will automatically dump the 7 bits in the latch into the upper 7 bits in the program counter, effectively writing all 15 bits of the program counter simultaneously. And of course you have to do that because it's going to fetch whatever the address is for the next instruction. And if you only wrote the bottom half, the upper 7 bits would be the wrong 7 bits, and therefore you'd fetch the wrong next instruction, and you'd screw everything up. So that's why you have to do it in 2 steps. Now, the good news is you don't ever have to do that. You don't ever have to write the program counter. You can use an instruction in its native instruction set that automatically does that for you, called a branch instruction. And there's actually 2 of them. One's called the go to, and the other's called a BRA, or branch always. So you can either write a go to or a BRA, and it will automatically take care of this for you. You don't even have to worry about it. We also have 4 what are called indirect registers, which actually make up 2 16-bit registers. But again, because we can only move 8 bits at a time, our indirect registers have to be divided into half. And it's the same thing. It takes you 2 instructions to get those indirect registers loaded up with a full 16-bit value. Now, if you don't want to change the upper 8 bits, then you only have to mess with the lower 8 bits. Or if you only wanted to change the upper 8 bits, you could just do that. But typically, you probably want to write all 16 bits. Or if you're maybe just incrementing it, you may just increment the lower 8. But the problem is, once that lower 8 rolls over, it's not going to automatically increment the upper 8. So you have to make sure that your lower rate isn't FF. When you add one more to it, it will go to 0, 0, and you should increment the upper 8 bits. And if you don't do that, but the good news is there are instructions that take care of this automatically for you as well. So you don't even have to worry about this. For purposes of this course, we are not going to deal with these indirect registers in assembly language. When you write C code, the C compiler automatically makes everything indirect addressing. So it uses these registers extensively. But we're not going to mess with them because it's a little bit confusing to use indirect addressing. And it's better just to use direct addressing, which is what we'll use. And then when we switch to assembly to C, then these indirect registers will be used all the time on your behalf, but you won't really even have to pay any attention to it because it all gets done by the compiler. There's another register that has 4 bits in it, and I think it has 8 bits, but there may be one that's not implemented. But anyway, there are 3 bits that are called the status codes or the condition codes, and they're in what's called the status register. There's also a couple of other things in this register that we'll talk about and that you may eventually need to use, having to do with interrupts and going to sleep and things like that, and power and brown out and power down, things like that. And then of course I mentioned this already, the register that contains your current bank, the bank select register or BSR. That's the programmer's model. And we'll look at that in just a second. I don't want you necessarily to become an expert assembly language programmer, because if we were going to do that, we teach you how to use the indirect registers too, because there's a lot of power in these. And if you really need to have continuous blocks of memory, you can't really do it without the indirect registers. But you can write some very powerful, very effective programs without having to get into the indirect registers with just a basic understanding of assembly language. And that's what I want you to have, so that you have a sense of how this processor really works, how it does its stuff, and how your C instructions get translated into these more rudimentary assembly language instructions. And I think that's very important for you to understand. And so that's why we're going to do this. Once we get past the first 4 labs, you can, except for a few questions on the test, you can forget about assembly language. Are there any advantages to assembly language? Yes, there are some. One of them is that in assembly language, you have total control over the instructions that the processor is executing. In C, you don't have that because your C instruction gets compiled into assembly by a compiler, and the compiler makes some assumptions. Not only that, if you pay more money, the compiler will do more optimizing. And so sometimes the compiler will look at your code and go, well, that was stupid. He didn't, this is a useless loop. So we'll just ignore it completely. And that's why when you're waiting on an external pin, you have to let the C compiler know that pin could change independent of any instruction, any software instruction. That's why you have to put in a special keyword volatile, so that the assembler doesn't, the compiler doesn't make any assumptions about the fact that pin will never change, and therefore optimizes away some of your code that you actually really do need. So that's one of the other issues. Sometimes your higher level language makes some assumptions that actually get you into trouble. And when in assembly, that doesn't happen. The other thing is, if you're a world-class assembly language programmer, you can probably always write your code tighter with fewer instructions, and it will run faster than you could in C, because again, you're constrained by the smarts of the compiler. Now, compilers have gotten pretty smart and they're very good at optimizing, but a really world-class assembly language programmer can still kick butt. And for some things, that's really important. Sometimes you want to push the chip to its absolute maximum performance, and you might not be able to do that. But here's one of the really nice features. If you know assembly language, you can actually write your C program, and then with a special syntax, you can slam assembly language instructions in wherever you want. You just have to obey some rules. And as long as you obey those rules and use the correct syntax, you can actually insert assembly language instructions wherever you want. And that's actually a nice, useful feature where there's some critical timing issues. You may want to write a routine that creates a new algorithm for reading a data line that's written in a protocol that for which there's not a standard module. Or you may have made up your own protocol. And you may find that when you write it in C, that there's enough variation in the timing that you're not happy. So you might have to write that as a assembly language routine, and then you'll actually just call that function, and you can call it from C, and the rest of your code can be in C, but that assembly language routine will still execute exactly at the timing that you designed, and you can be very confident of that. That is the case actually with Microsoft's touch sensing routines. On our chip, we have kind of their legacy touch sensing module, which works great unless you happen to have interference at just the wrong frequency, and then there's nothing you can do to fix it. For our purposes, it works fine. It works actually very well. But in order to get around that, they finally had to use special ADC modules that are called ADCC modules. They're computing converters as well. So they'll do things like average so many values and things like that. And these ADCC modules, they wrote assembly language instructions to implement the touch sensing application. So they don't even actually have a dedicated module. You just use the A to D converter. I haven't implemented it on this. I haven't changed chips, partly because of that. That's one of the things that's kind of caused me to stick with this chip. But otherwise, they use the same principles for touch sensing. It's just they don't use this module's now no longer in any of the current chips. They've gotten rid of it. They don't make it again anymore. This chip's not that old. It's only maybe 10 years old, or maybe 7. I don't know. It's not too old. Okay, well, probably 10. Okay, so I do want you to be able to write some simple programs. I want you to understand some of the limitations and some of the advantages of the assembly language. But the truth is, anytime you're going to do any complex algorithms, you're going to do complex math, you pull your hair out if you try and do it in assembly language. You really do need to use C. Math especially. Math is just, other than basic math, it's very difficult in assembly language. Of course, C does it in assembly language, but they have all these pre-existing routines that they take care of for you. Like just to have a 16-bit integer. In assembly, you can have 8-bit integers, fine. But if you want a 16-bit integer, now you've got to keep track of when you overflow, and you've got to increment the upper half, and even that, it gets to be a teeny bit of overhead. And anything more complicated than that gets to be crazy. Normally, if you actually were going to do some limited math in assembly language, you would use binary coded decimal. And we talked about that in logic design. That's why binary coded decimal was created in the first place, was to make it easier to do simple math in assembly language. But when you want to do fancy, complicated math with floating point numbers, and you're going to use IEEE 754 standard, just to get your number in and out of IEEE 754 standard is in and of itself a really, really big deal. So for anything, any real significant amount of math, you really have to do assembly language. I mean, a C. You really have to use C or some advanced level. Okay. Okay, so once you have a working knowledge of the integrated development environment called MPLAB-X, used to be MPLAB, they upgraded MPLAB-X, so forget MPLAB. You need to know how to create a project in assembly, create one in C. Now, interestingly, if you download the latest version of MPLAB-X, they have taken away the option to do an assembly language program that's easy. You can't do that anymore. You can still do it, but I don't know exactly how. It's complicated. So if you want to use assembly language, you have to stick with one of the older versions. And so that's why we recommend that you load up. I think 5.40 is the latest version you can do. 5.45, the assembly language assembler is gone. It's actually not gone. It's still there, but it's kind of hard to get at it, and it's not worth the hassle. Again, if you're going to write your code in C, no problem, then that's fine. well, you also need to learn how to create a simple C routine, how to add header files to it, how to add the main file, and then you need to know how the configuration words work. We'll talk about those a little more, but just for reference, there are certain words that get programmed into the program memory that set features of the processor independent of the execution of your software. And a lot of these you can change dynamically in software, but some of them you can't. And it has to do with setting up for the internal clock. And one of the things you want to do is make sure you keep it the programming set up so that it can be programmed with low voltage programming. Your Snap programmer debugger can change the bit that sets it for low voltage programming. And once it does that, which it can do, then your Snap programmer can't program it anymore because that means you have to have a programmer that can program it in high voltage programming, which the Snap doesn't do. So don't change that bit. I think we used to always set it for high voltage programming when we used a different programmer, but with the Snap, that'll screw everything up. So we'll talk about that, make sure you know about it. Now, if you do accidentally do that, it's no big deal. We just have to use another programmer and reset that bit, and you'll be fine, ready to go again. But your Snap can't get itself out of that predicament because once you set that bit for high voltage programming, your Snap can't program it anymore because it has to use low voltage programming. All the chips are always shipped with low voltage programming enabled on them. So unless you change it, your Snap will work. We use what's called ICSP, in-circuit serial programming. So you can also, this family of chips can also be programmed with, just like the Arduino can be programmed using a bootloader. But we don't use the bootloader. We use this in-circuit serial programming. And the reason we do that is when you use bootloading, you have no debug features. And that's why the IDE, the Arduino simple little integrated development environment interface, does not have any debug features. On our chip, you can single step the program. You can watch in your integrated development environment, you can watch each line execute. If you're in assembly, you get to see actually every single instruction execute as it executes. In the C, if you're following in your C code, remembering that each C instruction could be multiple assembly language instructions. So that could be the correspondence there is a little looser, but it'll still show you where you are in your C program. You can set breakpoints, and you can go in to the actual random access and program memory locations inside your PIC chip as it's running, and you can see you can stop it and look at any registry you want to look at, and you can reach in and change any bit anywhere in the random access and special function register area. I don't know if you can change the program. I've never tried to change the words in the program memory, but I think you can do that too, actually, if you want. So there's really extensive debug features, and that can be really helpful. The MPLAB-X also has a simulator. You don't even have to have your hardware. You can actually simulate it. You can have input files that get read. You can do a lot of simulation with the MPLAB-X environment for most of the microchip parts. Okay, let's see. Did we get through this? You should also understand how we put the Viva board together, why it is what it is, and what everything on it does. You should know why we have the bypass capacitors, while the RGB LED and the other two LEDs all have current limiting resistors for each of their colors. How we put in the UART to USB interface and how that works. How you can interface a push button using the jumper in the RB7 push button position and using the little button for that. And then we're going to have you interface a bunch of peripherals. We already talked about that.Ve got the little analog board that plugs in, where you're going to have a temperature sensor, a potentiometer, and a photoresistor. And then we're going to have you hook up the 2-line-by-16 LCD display and control it with I2C using a little buddy board on the back with a PCF 54 something or other, I forget. It's got a chip that does that for us. And so here's the basic architecture of our chip. It has program memory. Now, our program memory is only 8 kilobytes. You can have up to 32K of instructions. Remember, each instruction is 14 bits. So if you had 32,000 14-bit instructions, that'd be 56 kilobytes of memory if you're looking at 8-bit bytes. But in program memory, every single location is actually 14 bits. So this 56 kilobits is kind of a goofy thing. Just ignore that. The important number is in this family, you can have a maximum program size of 32K, that's a fair amount for an embedded design. The CPU, every instruction that's executed is always 14 bits. Now, there are many microprocessors that have variable length instructions, where one of the old Motorola chips, you could have an 8-bit instruction, a 16-bit, a 24-bit, a 32-bit. I think it could have as many as 5 8-bit bytes. So you could have a pretty good size instruction, or maybe even more than that. In the Freedom board that we use in Micro 2, all the instructions are 16-bit instructions, except there's 6 32-bit instructions. So they're variable length as well. But in this chip, the instructions are not variable length. They are fixed length, and they're kind of a funny number. They're not 2 bytes or anything like that. They're 14 bits. And they can do that because remember that the instructions live in a separate memory and with a separate address and separate data bus. So if you look at this, here's the CPU here in the middle. Here's the program memory over here with its red address bus and data bus showing things going to the CPU, but it's bidirectional, goes both ways. And over here, you have data memory, which has its own 8-bit data bus and 12-bit address bus. And you have all of the peripheral devices, all the peripheral IO drivers and registers are all on this same data memory area. They all have their own unique address within the data memory. And so we'll go over that. There's also a stack. Now, most of the time in most chips, the stack is implemented in random access memory. And typically the way it's done is your variables are stored at the bottom, building upwards in random access memory. And your stack starts at the very top of random access memory and pushes down. And as long as your stack doesn't ever run into your variables, everything's good. In this chip, it has kind of a unique thing called a hardware stack. It has a dedicated area of 16, and I think there's 16-bit locations, 16-bit locations that make up its stack. And that's also, the program counter is also in this little area. And what happens is when you jump to a function and then you're going to jump back, the return address is pushed on this stack as a 15-bit value in one of the 16-bit registers. So you actually have an extra bit. If you want to push a variable onto the stack, there's really not a good method for doing that. It actually can be done, but I don't recommend it, because if you jump into functions that call functions that call functions that call functions, and you throw in an interrupt on top of that, you can burn through all 16 levels of your stack, and that gets you to a reset or an error. So you don't want to do that, and that's why even though it's legal in C, it is illegal in this version of C, XC8, which is the C version we're going to use. XC8, it's illegal to nest, to have a function call itself. You'll see that as a cute programming trick, not that infrequently, but you can't use that cute programming trick here because it could easily recall itself more than 16 times. Like if it had a 32-bit number it was trying to crunch through, that could cause it to call itself 32 times. Well, there's only 16 levels of stack. So that's just not going to work. And once you start overriding the previous locations, you can never get back to where you need to get back to. So usually what it does, it triggers an error, but that's a choice you can set. But I don't know why you'd want it not to trigger an error, because it's going to screw everything up. Okay, so this is roughly how it's set up. And then we'll look down here in all the peripheral devices, and we'll see some of those in just a second. All right, so let's talk about the features of the chip. So the instruction set, 49 14-bit wide, easy instructions to learn. According to the data ship, they're easy to learn. So you don't have any excuse. And actually, they are pretty easy to learn. There are a few tricks. There's just one or two tricky, confusing points. And once you get those explained, you're kind of on your way. There's up to 32K of addressable program memory. In our chip, that is not the case. We don't have that many. I think we only have 8K. There's up to 4K of RAM, but in our chip, we only have 1K of RAM. So 1,024 random access memory locations. So you can't have more than 1,024 8-bit variables. In fact, you probably can't have that many, because a few of those RAM locations would probably be needed for other stuff. There is this 16-level hardware stack. And then you have the indirect registers, which we talked about. You could use those for other things, but we'll pretty much ignore them in assembly language. And when we write in C, you don't have any direct connection to them. C uses them all on its own automatically. You won't really see them or have any connection. There is interrupt capability in this chip, and it does automatic context saving. So when you're in a mainline routine, and we haven't talked about interrupts yet, but what an interrupt is, it interrupts what's going on in the chip and transfers control to a special routine. When it does that on this chip, it automatically saves where you were, the program counter address, but it also saves all the registers you were using. And when you return from your interrupt, it automatically restores all those. So that's really a nice feature. And it saves those registers in special addresses. Normally they would be pushed on the stack. The stack's not big enough to do that here. So, so they're saved in special, what's called shadow registers. But for that reason, you can only have interrupts nested. Well, you can't nest interrupts. Once you interrupt, you cannot interrupt again until you're done with that interrupt. And that's not true for a lot of other chips. Other chips have different priorities of interrupts, and you can interrupt lower priorities interrupts with higher priority interrupts, but not on this chip. And that's one of the simplification things. It just makes it a little easier to grasp what's going on and takes away some of the confusion. All right. So there are lots of nice features on this. Just a lot of very powerful modules. It's a pretty powerful chip. Okay, here's the programmer's model we just talked about laid out in pictorial form. Again, we have a working register. This is the W register. Every single thing that gets done on this chip usually has to go through the W register. If you want to do math, one of the add-ins has to be in the W register. If you want to AND something or something or exclusive or something, inverts. Well, if you want to do AND or exclusive or, you have to use the W register. If you want to yeah, I don't know. You can do direct operations on a memory location as well, but you can't take two memory locations and add them together. One of those has to be first loaded in the W register. You can't OR them. One of those has to first be in the W register, and so forth. So for all intents and purposes, the W register is involved in every single mathematical operation or logical operation on this chip. Now, the bank select register, remember we said that there are only 12 bits available for addresses in your data memory. 5 of those bits are in the bank select register. So that's why the upper 3 bits are crossed out. They don't really exist. There's only 5 bits in this BSR. And the lower 7 bits always show up in your actual instruction. So when you execute an instruction, the lower 7 bits of the address of, say, some memory location you're referencing or a special function register you're referencing, those lower 7 bits will be in the instruction, and the upper 5 bits will be in the bank select register. Now, how do you get them in the bank select register? You have to put them there. And if you don't put them there and they're not there, you have a problem. Now, the nice thing is there's some random access memory locations and some special core registers that are mapped into every single bank. So then it doesn't matter what the bank select register is pointing to, you'll always get to the right location. But other than those 16 memory locations that are called a common RAM and the core registers, which are the ones that are mapped in every bank, other than that, all the other special function registers, you must have the right bank address specified. And all other random access locations, you must have the right bank select register specified. Now, the only exception to that is if you use indirect addressing, which we're not going to do in our assembly language portion of the course. But if you were to use it, then you don't have to worry about the bank select register, because it takes all 16 bits here and comes up with whatever 12 bits it needs for the address. It maps it into the 12-bit address. And then finally down here, we show the 3 status bits in the status register. And again, there are a few other things in the status register, but these are the ones you have to pay that you're going to run into, at least in the early going. Okay. So I've covered most of this. So this is just restating things. So I'm not gonna go over this again. Here's also another way to look at it. We have one of the things I didn't say, I'm going to say it now. When you want to reference, if you were to use these indirect registers, remember they're divided into 2 8-bit parts. And they're file select register 0 and file select register 1. So those are the 2 indirect registers. And they're called file select register 0 high, file select register 0 file select register 1 high. So it'd be file select register 0 high, file select register 1 high, file select register 0 low, file select register 1 low. So each register would be like file select register 0 would be have a high and a low register associated with it. And since there are 2 of these, you have to decide whether it's the register 0 or register 1, whether it's high or whether it's low. And now remember, C uses these extensively, but you don't have to pay any attention to it at all. It takes care of this all automatically. And we're not going to use it, so you don't have to worry about it. But because it is set up this way, when you want to set this register to point to wherever you want it to point, you first load in one of the 8-bit values, you load in the other 8-bit value, and then you reference it with an entirely separate name. And that separate name is this, INDF0 and INDF1. And those are sort of dummy those are dummy core registers. They don't really exist, but they tell the processor you want to use the indirect information in indirect register 0 to go get your data or to do whatever you're doing. And it'll go do that. And that's so these are all the core registers. And there's actually another one called the interrupt control register that we're not going to really mess with. Well, we are going to use it, but we're not going to talk about it in the context of the programmer's model. The ones I want you to know about are programmer counter low, status register, bank select register, W register, and the program counter latch high. I don't care about you memorizing the incon register. Okay, so these are the ones I want you to do. PCL, PC latch high, status, BSR, and W register. That's it. Those are the 5 key registers that we're going to really deal with. Okay. Okay. Now, again, the BSR register. So the data memory is partitioned into 32 banks. And as long as you're not using indirect addressing, you have to have the BSR pointing to the right bank, with the exception of your 12 core registers and those 16 special RAM locations that are mapped to every bank. And we'll talk about that in a minute. But other than that, if you have information anywhere else, you have to be in the right bank. And each bank has 128 bytes. The first 12 bytes in every bank are the core registers. Same for every bank. That's why you don't have to worry about which bank you're in. The next 20 locations are special function registers. So that gives you 32 registers that make up either the core registers or special function registers. The next 80 bytes are always general purpose RAM, specific to each whatever bank they happen to be in. And then the last 16 bytes are also random access memory, but they're the 16 bytes of common RAM mapped to the last 16 bytes of every 128 bytes in every bank. So if you put your data, if you don't need more than 16 variables and you put it into 8-bit variables and you put it into common RAM, then you don't have to worry about messing with the BSR, except for some of the special function registers, because not all special function registers are in the 12 core registers. Most of them are not. Only a few are in those 12 core registers. And remember, 6 of those 12 core registers are the indirect registers, which we're not going to use per se. So there's only about 6 registers that you don't have to worry about. All the rest of the special function registers, you do have to worry about being in the right bank. And these registers are used to control all your peripheral modules and to get to your various external pins on the chip to connect to LEDs and other stuff. Okay. So again, the data memory is partitioned into 32 banks, each bank with 128 bytes. First 12 registers are the core, next 20 are the special function registers. Then you have 80 bytes of general purpose RAM that you have to be pointing to the right bank to get. Just like for the 20 special function registers, you have to be pointing to the right bank for them as well. The 12 core registers are at all banks, so you don't have to worry about the banks. And the upper 16 bytes of common RAM are mapped across all banks as well. The active bank, of course, is selected by writing the bank number into the bank select register. It will be a 5-bit number because there are a maximum of 32 banks, 0 through 31 are how they're numbered. Now, if you want to have a block of RAM that's bigger than these continuous 80 bytes, then you have to use indirect addressing, because otherwise it would break across one of these memory banks, and it would be very tricky to write a routine to take that into account. I guess you could. So here's what that memory looks like. This is a bank. First 12 bytes are the core registers. Next 20 are special function registers. Next 80 are general purpose RAM. Next 16 are, the next 16 bytes are common random access memory. And if you go into a mode where you're, if you want to save a little time, you probably should take advantage of common RAM when you write your program most of the time, because there's no reason not to use this 16 bytes for your variables, right off the bat. Again, if you're working in C, then you don't have to worry about this. It doesn't even use this. It uses indirect addressing, so it doesn't deal with the banks per se. The indirect addressing pretty much skips the banks. The hardware maps these the indirect addresses to the right location. Okay, indirect addressing. I'm not going to talk about this. Same. Okay, status register. So the 3 bits I want you to be concerned with are the 0 bit and the carry bit, and then this middle one called the digit carry bit. The Z bit is set to 1 whenever the register you're dealing with is gone to 0. And not every time that you mess with a memory location does it set the Z bit. You have to look and check and see. If it doesn't say that it does, then it doesn't. Then the digit carry bit has to do with binary coded decimal mathematics, and it lets the programmer know that there's been a carry from when doing an add operation. There's been a carry out of the lower four bits, which we call a nibble. When you have a carry out of the nibble, the digit carry gets set so that you can adjust the nibble correctly and then add 1 to the higher order nibble, or it's already got its carry, I guess. And then this is the standard carry. This is what happens if you do unsigned addition and it adds up to more than more than 256, then it'll cause a carry out, and the carry bit will be set. Now, if you're doing 2's complement math, you ignore the carry bit. But if you're doing unsigned math, you have to pay attention to it. If you're doing 2's complement math, then you have to pay attention to, well, what we would call the V bit, which doesn't exist on this chip. Many chips do have a V bit, but this one doesn't. But the whole V bit is set up when there's a 2's complement overflow. 2's complement overflows, if you remember, when you add 2 positives and get a negative, or 2 negatives and get a positive. If you add a positive and negative, you can't overflow, so there's no problem. But you're the one that has to know whether you're dealing in 2's complement or unsigned math. And again, you shouldn't try and do too much math in assembly language, because it is so much more difficult than in C. It's much better to just do it in C. There are 2 additional bits. One of these is the timeout bit, and the other is the power down bit. We are going to use the timeout bit when we do the sleep lab later on, but the power down bit we probably won't pay much attention to. Okay, so now we're going to just look at some assembly language instructions and sort of the syntax and what they look like. And let's see. Yeah, we've got about 15 more minutes. So I might come back to this in a minute. I think I want to go through the instruction set to start with. But let me just say a couple of things. First, any assembly language instruction is made up of basically 4 things. There's an optional label, and only the label can be in the first column. Don't put anything else in the first column. You'll get an error. So you have to space in before you write your opcode or any of your operands. So you have a label, if you have one. If you don't, then you space. And usually I put labels on separate lines. So effectively this start label is really on this bank cell line down here. Now, the bank cell word itself is not an instruction, it's a compiler directive. And it tells the compiler to do something. Or again, in this case, it tells the assembly language, the assembler, to do something. We have compiler directives in C. We have assembler directives in assembler. And in one of the compiler directives in C is an include statement, to include an include file, or to create a variable, or whatever. So, or a function prototype, or that sort of thing. But in assembler, we have other assembler instructions, and this bank cell is an example of one we're going to use very, very frequently. What the bank cell does, remember I said you as the programmer have to make sure you have the right information. You have the upper 5 bits of the address in the bank select register. Well, this bank cell instruction, and then you tell it what variable you want to be correctly located by in the bank setting, and that's how you do it. You say bank cell OSCON. OSCON stands for the oscillator control register, and that's where we program in the frequency we're going to run the chip at, using its internal oscillator module. And we've just sort of arbitrarily chosen a nice happy medium of 4 megahertz. It can go up to 32 megahertz, but we're going to run it at 4 megahertz for most of the time, and maybe even all the time. And that works out to be, so we can get good PWM settings, but it's also pretty quick. So we just like 4 megahertz. So anyway, so we want to put this hex value of 6 alpha in the oscillator control register to set it for 4 megahertz. To do that, we want the upper 5 bits of the oscillator control register address correctly set in the bank select register. And this instruction, this assembler directive does it for us. It causes the assembler to generate a special instruction to put the upper 5 bits of the OSCON address into the bank select register. And we're going to use this lots and lots and lots. So it's very helpful. You see, we use it again here to put the TRISC C register into the upper 5 bits of that address in the bank cell. And here we do it for port C. So we use it 3 times in this short little program. We're going to use it a lot. And there are other compiler directories we're going to introduce. There's a whole bunch of them. You only really need to know a handful. Just like in C, there are a lot of compiler directives that most people never learn because they don't write modules to be used in libraries and things like that, where typically you need to use a lot of those. Okay. All right. So here's an example. So we first have the label, in this case, start, can be on a separate line. Then we have our opcode. So the bank cell is not really an opcode, it's a compiler directory. But here's an opcode. So here there's no label on this line. And then there's MOVLW, move literal to W. And then we have an operand. You can have up to 2 operands. This instruction set that has no instructions with more than 2 operands, and many, but quite a few with 2 operands, and then quite a few with just 1, and some with none. In this case, we only have 1 operand here, and that operand is a hex number 6 alpha, which is an 8-bit value of 011011010. That's what it is for the 8 bits. And what it's going to do, it's going to take that value and it's going to store it into the W register. And then the next instruction, MOVWF, that's going to take what's in the W register and put it into the file register that you specified. And here we specified OSCON. So that's going to program OSCON to be set to run on the internal clock at a rate of 4 megahertz. Then we're going to bank cell the TRIS register and clear it, bank cell port C and clear it. And that just kind of gets things set up, ready to go. The IDE will format these things for you. And then, so the last field is your comment field. If you want to have a comment, you don't do // you use a semicolon. A little kind of crazy. I know, C uses semicolon to be the end of the instruction. In PIC assembler, in XC8 assembler, you don't have to do that, or not XC8, but in MPASM, you just hit a carriage return, it automatically terminates the line. So, but if you want to add a comment, there's a room for a comment field preceded by a semicolon. Okay, so those are the 4 fields: label, opcode, operand, 1 or maybe 2 operands, and then a comment. The label is optional, the comment's optional, and the instruction may or may not need any operands at all, or maybe only 1. Okay, so that's kind of the rough syntax. Now, let's look at the instructions. So we have several groups. We have what are called byte-oriented instructions. We're going to come back and look at those. We have byte skipping operations. We have bit file operations. We have bit and bit skip operations. And we have control operations. All our control operations have to do with branching. And instead of in assembly language, we don't call it falling, but we just as easily could have fallen. We call it we don't call it. I slipped the cog there. We in assembly language, we don't call our functions. We call them subroutines, but in C we call them functions. But they're basically the same thing. So here we have a call subroutine. This actually harkens back to the old days when we didn't call functions, we called subroutines. And back when we wrote programs in Fortran, we called subroutines. And when we wrote an assembly language, you always called subroutines. A subroutine is just a function. And the only difference is you have to have a specific call statement for the subroutine, whereas in C, you just write a function name and you're automatically calling it. So the call is assumed in C, but it's not in assembler. Here are the 2 branches I mentioned, the BRA and the GoTo. Now the BRA can also be relative with the W register. I've never used that feature, but you can. So you can have an offset in the W register that gets added to the branch before it's taken. Both of these branching registers, the BRA and the GO2, are 2's complement branches. So wherever they appear in the code, you can be branching further in the code or backwards in the code, depending on whether you have a 2's complement positive number or a 2's complement negative number. So they are considered signed. And that therefore, the biggest number you can have depends on how many bits are set aside. For the BRA, we have 9 bits set aside. That's the little K. For the GO2, we actually have 11 bits set aside. But remember, that's 11 bits of signed, so you only really get plus or minus 10 bits. And 10 bits is 1K. So with the GO2, you can only really go plus or minus 1,024 instructions in either direction, which if you have 8K of a program, which we have 8K of program memory, if you have all 8K filled up, you can't branch from the beginning of your program all the way to the end of your program with a single instruction. And that's maybe the one time where you might actually have to use the PC latch high and then write the lower, the program counter low to actually do the branch. But an easier way to do it would be to branch to an intermediate point and then branch from there and branch from there. And you can set those up within your code if you really had to do that. But normally you wouldn't have to do that. But you know, if you wrote a really big program, you do have to, you have to kind of keep that in mind. But here's the nice thing. C takes care of that for you. C is smart. It takes care of that for you. So, but if you wrote a really huge assembly language routine, then you might have to deal with that. Okay. And then we have return from interrupt, and then this return with literal and W, or just return. So this return with literal and W does not apply to the interrupt routine. It only applies to the subroutine. We never return anything from an interrupt. We never send anything to an interrupt as far as variables. We never pass anything. We never return anything. And that's because you never know when it's going to happen. And so there's no way to do that. But with a subroutine, you can call a subroutine and it'll preserve the value in W. You can, and I forget that, I don't think that uses, that may use the W as an offset too, actually, come to think of it. So we don't really pass values to subroutines in assembler, and we don't return values from subroutines, except we can return one literal and W. So you can do that. All right, but not from an interrupt. So you can either return from a subroutine without anything in W, or you can return with a literal in W. And here you specify that literal, and it's an 8-bit value. All right. And these are operations we probably won't use: a no op, clear the watchdog timer. And some of these are legacy, the option, sleep and tris. Well, sleep's not. Option and tris or legacy instructions, you don't have to do those. You can go into a software reset mode. You can go into you can force the chip into sleep mode. We will do a sleep study, but we'll do that one in C. And then these are some instructions that are used by the C compiler. We probably won't ever use these. They're kind of specific to the C compiler. Okay, so those are all, I guess those are all. I didn't see, yeah, bit skip. Yeah, bit skips. Okay, right. And then literal operations. All right, I think I went over them all. I think maybe I skipped these somehow. But anyway, you're going to see these bit set, bit clear F, and bit set F, and we'll talk about these. I'll explain all these instructions, but I think well, let me try and explain the instructions. I'll do that. That's probably a good use of the next 3 minutes. Maybe I'll stop here in a second and see if you have questions. All right, these byte-oriented instructions have two. Almost all of them have 2 operands, but the ones that don't have 2 operands are the ones we use most frequently, it turns out. The move W to F does not have a second operand, and the clear F does not have a second operand, and clear W doesn't have any operands, but all the rest of them have 2 operands. Now, what is that second operand bit, and how does that work, and how do we fit an opcode and 2 operands into 14 bits? All right, here's how this works. This first operand is an F, And all of them have it except for the clear W, which makes sense because clear W is going to clear the working register, and you know where that is. You don't have to specify it. But every other one of these instructions, you have to tell it what special function register or what memory location you want to operate on for that instruction. So if you want to add something to a memory location, you're adding the contents of the W register to a specific with the contents of a memory location or a special function register, and then you're going to store it. Now, where are you going to store it? It turns out this second operand tells the instruction where to put the results. And that's now, if you look over here where you see the actual 14 bits, notice that you have, for this add W to F, you have 000111. That's the opcode. The opcodes can be different lengths. In this case, the opcode is 7 bits. In this, the opcode is 6 bits. And then you have a D bit here, and you have 7 bits of F. But there's only one, and if you look down through here, there's never more than a single bit for D. So this second operand is only a single bit. Therefore, it can only communicate one of two things. And here's what it communicates. You either leave the result of the operation, in this case, you add W to the file register, and you leave the contents of that in one of two places. One place you leave it in the file register, and the other place you leave it in the W register. Those are the only two possibilities. If the D bit is a 0, you leave it in the W register. If the D bit is a 1, you leave it in the file register. And if you don't specify the D bit, the assembler will make it a 1 by default. So you'll leave the result in the file register, not the W register. So remember, when you want to move one location in memory to another location in memory, you can't do it in a single instruction because you only can reference one address in memory. And the second operand is not room for a second address. It's only a single bit. And it only tells the results to be left in the W register or the reference file register. Now note, I said that in data memory, you have a 12-bit address, but look, there's only 7 bits of F. 1, 2, 3, 4, 5, 6, 7. So if you only put 7 bits of a 12-bit address in the instruction, where are the other 5 bits? And the answer is the BSR. The other 5 bits have to be in the BSR unless it's one of the core registers or the common RAM, the upper 16 bits of RAM in bank 0 mapped to every other bank. Okay. So here you have an add. Here you have an add with carry. So it adds the W, the contents of W, the contents of F, and the carry bit, whether it's set or cleared. Notice this column says status affected. This tells you what bits are impacted by the instruction. And only these mathematical operations and a few others, the shift operations affect the carry bit and the 0 bit. And then these add and subtract operations do affect the digit carry. None of the other instructions pay any attention to the digit carry. And you should look through these. You have add with carry, and shift right, logical shift left, logical shift right, clear, a compare, decrement, increment, inclusive or, exclusive or, swap nibbles. That's not swap bytes, it's swap nibbles. The lower 4 bits gets switched with the upper 4 bits in either W or a file register. Well, the results get left in a file register or a W. But you could specify W, I guess, if you wanted. Subtract with borrow, subtract W from F. Subtract with borrow just means you use the carry bit. Rotate through carry right, rotate through carry left. And then the most important one is move W to F. So you take the contents of W register, you store it in a file register. And here, move F, you take the contents of a file register and you store it in W. But look, this does have the D bit, which means you can specify the W register or you can specify a file register. Why would you want to move a file register back to itself and never put it in the W register? And the answer is over here in this column, because it does set the Z bit. So it's one way to test if a contents of a file register happens to be 0 or not. But that's the only use for that. Otherwise, you'd always want to specify a 0 here, or instead of putting a number, you can write for the D bit, you can put a W or an F. W means it's going to leave it in the W register, and F means it's going to leave it in the file register. It can be upper or lowercase. Okay, I'm going to unshare my screen. And so we're at 2:18, 3 minutes over. So I'll give you a second for questions if you have any. I know some of you may have other classes you have to switch to. So let's see. Yeah, good. Don't want to do that. All right, let me go back to the view.
Sir, for homework 1, are we using the MC9 datasheet under course content?
For the homework, are you using the what data sheet?
It's labeled MC9 S12G128 datasheet under course content.
Okay, what you're using, it should say PIC 16F 1829, or it's actually PIC 16F 1825 or 1829. That's the data sheet. So I don't know what, I'm not sure what, I have never heard the designation you're talking about. Let me pull up the website and see, because that doesn't compute. Okay, so course content. Okay, let me look real quick. Okay, so where did you see that? Is it on here?
Yes, it's under course content. It's highlighted blue about 2/3 of the way down.
No, this is an old Freescale chip. That's not what you're using. So let's see if I have the PIC. I think I have the PIC data sheet on here. I think it's a little further up, but let's look. Yeah, I probably should delete that other one or hide it, because that's what we used to use, but we don't use it anymore. Let's see. I think the data sheet's probably under the lab page, actually. I don't see it here.
Yes, it's under the lab board.
Yeah, you just have to go in the lab folder. Yeah, right here. Click that, and then you'll see, let's see, where is it? It should be down here. Yeah, PIC 16F 1825/29 data sheet. And this is what it should look. It should be a microchip product. The other one was a Freescale product or a Motorola project. So yeah, totally different. All right.
Yes, sir. Thank you.
Yeah, sure. Good. That's a good question though. I'll make that invisible. I haven't gone through and I haven't curated all the websites yet. It takes between the syllabi, copying the courses, and then setting all the dates in the web sheet. It just takes me a week to get it done, or maybe 10 days. And you can't start very far ahead of time, because you have to wait till they set up the courses and populate them with the students, and then you can do course copy. And anyway, it just takes a while. And you pretty much find yourself doing it the first week, no matter what you do. Any other questions?
I have a question.
Sure, go ahead, James.
So I did not actually receive the email at all. And even the one that was from the test one, right? And that gives me a little concern, because that's how you're going to be giving out your lectures, right? So
yeah, so I've never actually done it, but I know somehow you can go into Blackboard and fix your email.
I've checked, and it's actually the correct email, and I just still haven't received anything. And I checked ASAP.
How about your junk folder?
I tried my junk and spam.
Don't know what to tell you. Then maybe you should set up a different email account in Gmail or something and send them to that.
Okay.
There's probably a non-printing character or something screwing it up. I don't know.
Okay. Sounds
Yeah.
good.
The other thing you can do, feel free to call 210-458-5555 and tell them you think you have the right email address on Blackboard and it's not, and you're not getting email. What's up?
485.
Yeah, 485-5555.
Okay, cool.
Yeah, but maybe, I don't know. But anyway, yeah, you need to fix that, because that is how I will communicate with you.
Okay, sounds good. Thank you very much.
Yeah. Any other questions? Be sure and bring $10 on Friday. I'll probably send that out in an email tonight. So it's a pretty good deal. Go ahead.
So you said bring $10 on Friday. That's going to be in person.
Yeah, yeah, come to the lab and get your Viva kit. You can solder it together.
Okay. Okay. And
Yeah,
if you already have a Viva kit.
Yep, we had students come over a couple weeks ago and we stenciled, pick and place and reflowed 90 some odd.
Okay.
So we got them. What I don't currently have, unless it comes in today, is all the snaps. But the $10 will cover that. When they come in, we'll just hand you one.
Okay, sounds good.
I mean, we'll check it off, but we'll hand it to you.
For the soldering iron, are we able to use it over there?
Yeah, you can bring your own, but we'll have soldering equipment set up. Yeah.
Are we gonna use that?
And like I said, I hope to set up some over in the makerspace, and we'll see, hopefully that, but yeah, if we don't do that, we'll set some up upstairs in the 3rd floor lab, unless they have people up there. And if that's the case, then we might set some in the lab that's next door to the 22 lab, but we'll probably just use the makerspace because that's what it's for.
I just want to say, Professor, I emailed you when I wasn't able to get into the lecture because the email with the link was a bit buried in my inbox. So I just wanted to let you know that there's going to be like 2 emails from a confused student. That's me. And I just want you to
Yeah,
let you
no
know
problem.
that you can ignore those.
Okay, no problem. I'll probably respond to them because I'll forget, but that's fine.
So I have a question.
Sure.
I'm a little confused about what we talked about today. Is that normal for starting this course, or is there something I need to be studying?
It's normal. Yeah, I'll go over it. I'm going to go over it multiple times. And this, I just tried to dump the truck on you today, and then I'm going to go back and spoon feed it.
Okay, thank
So
you.
don't worry. I suspect everybody's a little confused, and some people probably fell asleep. I'm sorry, but
Actually, almost did.
yeah, but I know it's a little tedious. I get it, but you'll pick it up. But we're gonna when I first started teaching this, I had a very difficult time teaching assembly language, but I will go through it. But it's a lot easier if I do it in person on the board, and so hopefully we'll do some of it. But you can always, I'll post this video, and then you can always go online and look at the other video from previous semester. So you can, if you look at them a couple times, it may begin to sink in, but it is complicated and it's a little tedious, but once it clicks, it'll be okay.
Okay,
Yeah.
thank you.
So I expect you to be confused right now, and I apologize for that, but it's kind of goes with the territory. Yeah, and that's why you have to do the lab. The lab is how you learn this. When you finally sit down, type in your own instructions, run the chip, and you say to the TA, Alex, it doesn't work. Well, no, because you didn't do this. Oh, okay. And then next time, Alex, it doesn't work. Well, no, because you didn't do that. Oh, okay. And eventually you make all the mistakes and then you figure it out. It's a little tricky. It's hard. It's really hard to, it's hard to bootstrap yourself into your first microprocessor programming experience, and especially in assembly language. It's hard. Go ahead, Isaac. Anybody else have a question?
Yes, sir. I have a question. I tried to access the quizzes related to the lectures.
I didn't turn those on, but I'm still thinking about whether
Yeah, there's
I want
no
to.
quizzes.
Yeah.
Okay.
Yeah, because I don't know. I mean, if you think you guys would like to do them, I mean, you could do them just for fun. If you'd like to do that, I'll turn them all on. Yeah, that might be good.
That's fine. Okay.
Yeah, they're
Okay.
short. They're only 4 questions, and it's maybe a good experience to see if you figured it out. Yeah, okay. Maybe I'll go through and turn them on so you can just practice on them. Yeah,
Yeah. Okay.
yeah, it's not a bad idea. I hadn't really decided how to handle that. That was really for when the course is just only online. Because I knew if I did the quiz, it'd kind of force the students to look at the videos. Otherwise, they wouldn't look at the videos.
Maybe since it's in person, we don't really need the quizzes. Maybe make them unlimited attempts. That way,
Yeah,
we trial and error if we need to.
yeah, I'll do that. I'll make them. I'll turn them all on. I'll make them unlimited attempts. You can see them anytime you want and do them.
I do have another question.
ahead.
Sorry, I apologize if this was something that was already asked that I might have missed. But in terms of getting help for this. I remember having a bit of difficulty asking the tutoring center
Yeah.
a previous time.
Yeah. So did you take the course before, James? Was that right?
Yes, I had to drop it though.
Yeah.
So
Come to lab.
come to lab.
Come to lab. In lab, I'll be there a good part of the time. Alex will be there part of the time. John Chung will be there part of the time, and they can help you. We can help you. And all you have to do is ask the questions. Tell us, I don't get this. Here's what I've done. It's not working. We will fix it. We'll help you figure it out. We'll point out where you're off. I've had every single possible screw up that could ever be done has been done. I think. Well, you guys may come up with some new ones, but the vast majority have been done. And we can usually figure it out. And in all honesty, you need that because it's hard to do this on your own. And so that's why I really pushed last year for face-to-face lab, but then the university told students you don't have to show. So we were there, but nobody came, or hardly anybody. And a lot of students had trouble with it. Not everybody, but I gave 20 incompletes last fall. So, which made me sad. I didn't like that. In the spring, I just flunked them. There wasn't any point in doing the incompletes because people didn't make them up in the spring. So anyway, so come to lab, and we'll help you. And what you're going to find is it's going to be a little bit tough the first few times, but as you start to get a sense of how this works, you're going to get very excited about writing code for your microprocessor, and you're going to have fun with it because this is what you wanted to do when you grew up. Remember, and it's really exciting when it works. It's really exciting, and it's very frustrating when it doesn't work. Yeah, great.
Dr. Moore, I have a question.
Go ahead.
So I know that you said that the prerequisite quiz wasn't for a grade, but on
Right.
Blackboard it is. Is that something to worry about or no?
No, Riva, they're only graded so I can report scores to ABET.
Oh, okay.
They're
Okay.
not graded so that I can apply it to your record.
Okay. I just wanted to be sure. Thank
Yeah, no
you.
problem. No, I expect you not to do well on the prereq quiz. That's the whole point.
Okay, thank you.
And we'll see you at the lab for tomorrow at 10, correct?
Yeah. Anytime from 10 to 3. If you miss tomorrow, you can always, you can probably catch us in lab for DSD. We'll be in DSD lab Monday at 2, Tuesday at 11:30, and Wednesday at 2. And you can probably pick up a kit then if you don't make it up tomorrow. So, but I'd like you to make it tomorrow and then hopefully do some soldering on your board, hopefully get your board ready to go. So next Friday, a week from tomorrow, you're ready to do the first lab in person in the lab. That's what we're hoping for.
Okay, perfect.
And I again, I promise if you just push through a little initial confusion, you're going to have a good time with this.
Yeah. I mean, I kind of felt bad earlier, kind of like what the other student said. I kind of agree with him. I was also confused, and I recognized some of the things from logic design when you were referring to the gates, but almost everything else, it sounded like it was just like a new concept. So
I understand. It'll all start making sense. This is, it'll all start making sense. But it is a little. The first thing you have to realize is that the electronic devices you've been using, including your cell phone and computers, this is how they all work. But you've been using them at a very high level of abstraction, and what's been going on under the hood has been magic. Now you're going to get a look at the magic, and it's not very magical. It's really one bit at a time. It's hard. Mm-hmm. It's grinding it out the hard way, and you're going to say, "My God, that's how this really works." Amazing. And then you're going to realize, no, you're going to be one of the engineers creating the magic.
Right. Well, here's to that. Hoping it'll
No
be happening
problem.
soon. Well,
No,
I
you will
appreciate it.
be
Thank
fine.
you.
Okay, one last question and we'll quit. Anybody
All
else?
right, see you tomorrow.
Okay.
Yeah, I just had one question. So I know that we're getting together tomorrow for the lab. Is that going to be every Friday that
Yeah.
we're doing the lab?
Every Friday.
Oh, okay. Yeah,
Yeah,
because
from
I
Every
think
Friday,
that,
10 to 3. So you don't have to come in the same time. You don't have to come in your assigned time. But you should try and come in every Friday. Now, if you work from home and you figure it all out, you don't have any problems, and you just want to pop by the lab for 2 seconds and demo and take off, that's fine. You can do that. And I do encourage you to work from home, to download the MP Lab and have it running. And we will, I want you to download it. There's certain versions we want you to do. So I'll make that crystal clear. I'll send that out in an email. I think, I can't remember if I put that in the syllabus or not, but some of the more recent versions of MPLAB X drop the assembler. So you can't even do the assembly language in them. Once we get past that, you can do the C, but the other thing they force you to is you need to get the right version of C. The later versions of C change the naming conventions a little bit and make it difficult to move files around with impunity. So I've generally hung with some of the versions of C that are a couple of years older, but you can't go back to really old versions of MPLAB either because they won't recognize the snap. So there's kind of a sweet point for your purposes for this semester. All right, with that, we'll quit. We'll see hopefully most of you tomorrow picking up your Viva kits. Like I say, we probably won't have the snaps. But you won't need them until you're ready to program the computer. All right, we'll talk to you later.
Bye.